let's start to get the hang of antiderivatives or integrals. So let's just do a series of examples. So how about this number 1? And I think let's do it in, write out the actual integrals. So what's the integral of 5x squared minus 2? And we should put the dx in here, because really whenever you see that integral sign, there's got to be a dx with it, otherwise it doesn't make sense. Now, let's look at the first term. What's the integral of just 5x squared? So think of limits. You can pull the 5 out. The integral of x squared is x cubed over 3. So it's simply 5/3 x cubed. And what's nice about this is you can see in reverse that if you take the derivative of this term, the 3 comes in front, those 3's canceled, and you're left with 5x squared. And this would simply be a minus 2x. But if there's no bounds, you need to put in the plus c. Okay, so all these antiderivatives should have a plus c. Now let us look at another one. Okay? Consider the following. What if we have the square root of t minus t to the 4th plus 1 all over t? And let's say that this is equal to f prime of t, and then we want to know, well, what's f of t? Okay? So there's some different ways you can express this, right? If this is the derivative, then clearly f of t is the antiderivative or the integral. Now, to do this, I think you first want to express this in a way that's easier to deal with, okay? We're not doing any sort of product rule, quotient rule with integrals, okay? Techniques are coming later. But what we can do is divide these terms by t, and let's first say what f prime of t then should be. Was t to the 1/2 over t, that's going to be t to the negative 1/2, and then this is going to be minus t cubed. And this will just be, we're dividing t into each term, so this is going to be plus t to the negative 1st. And now it's much more easier to determine what f of t actually is, because we can take it one term at a time. Now what we've been doing sort of consistently here is if you have, say, x to the n, and you want to know, like, what's the integral of x to the n dx, okay, well, it's x to the n plus 1 over n plus 1. You certainly have this plus c. So, right, why? Because you always go up a power when you're integrating. Derivatives go down a power. If you take the derivative, put the n plus 1 in front, they cancel, subtract 1, and you're just left with n. So it's clear that this, in fact, is correct. Okay, so for f of t, then, even if it's 2 to the negative 1/2, we still just add 1. You add 2 halves. That's t to the 1/2, okay? But then it's divided by 1/2, which is the same as times 2. Similarly, this will be, you add 1 t to the 4th over 4. And then for t to the negative 1st, right, if you add 1, what do you get? You get 0. Whoa, wait a minute, issue here. Yeah, because what's the integral of 1 over x, dx? You've got to think, okay, the power rule here doesn't work. Do we know of a function whose derivative is 1 over x? We do. It's the natural log of x. So actually this is plus the natural log of t. And then because it's a general function, we need this plus c. And c is just any arbitrary constant, right? And do keep in mind, the whole reason why this works is because when you take the derivatives, you should know how to do this. A constant goes to 0, ln t is 1 over t. You can check the others, right? Like the 4's cancel, left with t to the 3rd. And so it's a little trickier to check. I will leave that one up to you. Okay, let us do another one. Just keep going. What is the integral of secant squared theta d theta? Is there a function whose derivative is secant squared, it's tangent, right? So sometimes you might have to think of a particular function. In this case, it's the tangent of theta. Once again, we need that plus c. I may have forgotten a plus c in a previous video. It happens. People forget the plus c's. Everybody does. And you'll see why, because we're not always going to be using them. You'll see examples when we plug in numbers, we don't actually need that. Okay, so we'll just do a couple more. What if we have the following? What if we have, say, the acceleration of a function is given by, let's say it's sine of theta minus 2 cosine of theta. And then we want to know what's the velocity. Okay, well, the idea here is that because the derivative of velocity is acceleration, we need to integrate to get the velocity. So it's simply integrals. So derivative of integral of sine is actually cosine, but negative. It's be negative cosine theta. And then the 2 just comes out front. It's going to be minus 2, and the derivative of sine is just cosine. Right, so it's actually sine theta. Okay? So hopefully you're getting the idea. You're basically just applying power rules. Or you're doing some kind of interesting sort of thinking about what's the function that gives me this derivative, like secant squared and tangent, 1 over t and ln t. And then you might sometimes put properties together, like with velocity and acceleration. Now, I actually want to do, say, a final example that sort of is connected with the one above it. And this is the following. We're going to derive Newton's laws at this point, laws of motion. So what's the acceleration? What if you have constant acceleration? Okay, can we just get the velocity from this? Now it turns out that you can, right? We just had a problem like this. You just integrate. And so if a is a constant, some number, then we know that the integral is just that times the variable, right? Because if like the derivative of 3t is 3 and negative 2t is 2, negative 2, then at would be a, so it's just at. But what about the constant? Now this is interesting. We could put a plus c, that's actually okay, but what happens when t is 0? When t is 0, there is no acceleration, right? V of 0 is just c, the constant. And so when the time is 0, that's a special constant. That's the initial velocity. And in physics, you would mark that with a v naught. So it's the velocity at your initial time. Okay. Now what about the position? Can we get the position here? So once again, we're going to integrate, because you've got to integrate to go from acceleration to velocity, and again from velocity to position. And so now we apply the power rule, because t, it's like t to the first, you've got to go up a power to get t squared over 2. You just pull the a out front. So it's a, because why? Because it's limits. And limits allow you to pull constants out front. Always remember it's limits. And that helps you kind of figure out what you can and can't do. So it's a t squared over 2 plus v naught is a constant, so it's just times t. So v naught times t. And now we've got another constant. And so, right, it's just a plus c. But again, if you plug in t equals 0, these terms all go to 0. It's your initial position. And if that is like s, sometimes it'll be x, it'll be s naught. Okay, so these are, like this is one of Newton's, these are Newton's like laws of motion. Like this right here, you need to understand integration to be able to get that. And just to give you a practical example, right, like a is known to be, like if you know, okay, let's just do this here. If you know, so for instance, a, if we know that the acceleration is 9.8 meters per second squared, which it is on Earth, okay? That's the gravitation, that's the acceleration that all objects, including me and you, feel due to the gravity of the Earth. Okay, it's 9.8 meters per second squared. If you drop something, that gives you the equation of motion. So if you want to know where is the object, if it's falling, you can get its position at any time using this equation, right? So in effect, you integrate twice. And I mean, we did it already, but to do it with an actual number, it's 9.8t, but then you've got to do it again. It's 9.8t squared over 2, which is 4.9t squared. And then v naught here, now this is interesting. What's your initial velocity? Let's say you're dropping it. Okay, if you drop an object, we'll just say that's the case here. And so you drop an object. If you drop an object, the initial velocity is 0. Okay? So that term will go away. And when you're dealing with coordinates in physics, you can actually pick where's your 0, right? And if it's at the top of the building, which I would recommend here, so it's right, like here's a building, and someone's going to drop something off the building, you can say that this is where s or x equals 0. And then if that's the case, that's also 0, and this actually is the equation of motion. Okay, so this is like sort of a 1 and a 2 here, I guess. Two different ways that you could look at it. I mean, the first case, it's more complete. And the second gives you the full equation of motion. You know, dropping any object where the Earth is sort of your gravitational field. So what we're doing here is sort of tying together a little bit of physics and a lot of antiderivatives to kind of get a feel for what it means to take an integral, okay? And what we did over here, which you'll get more practice with when you much later in the year when you see differential equations, is sort of looking at initial conditions. Because what initial conditions can do is they will give you the constants. And so you can add some conditions here to fill in what is C, okay? And maybe, like, just for instance, it's plus C, and so, you know, if you have some condition, okay, some condition on this one, so let's say you've got f is 1 over x, sorry, f prime is 1 over x, but then you've got, well, f of 0 is 2, okay? So how would you do that? You say, okay, well, first of all, what's f? Well, I take my antiderivative, and that's the natural log of x, but then I know it's plus c. Okay, well, f of 0 is 2, so you plug it in. I think I meant not f of 0, because if you plug in 0 here, there is no natural log of 0. It's actually undefined. So let's try f of 1, because that gives you 0. And so if we plug in f of 1, now the result is 2. So 2 equals, and you plug in 1, ln 1, in parentheses, I guess, plus c. But the natural log of 1 is 0, because e to the 0 is 1, and so that's how you would get 2 equals c. Okay, so you can have these initial conditions. Okay, you also see them, we talked about them in these two examples, to actually fill in what your c's might be.